Hello, dear students. Glad to meet you again in this session. In this session 1.4, we are going to discuss about uncertainty in measurements in the same chapter number 1, some basic concepts of chemistry in grade 11. Before getting into this session, students, let us recall all the topics that we have discussed so far. In the first session, we have discussed about importance of chemistry and nature of matter and its classification. In the second session, we have discussed about 7 basic units of SI system. In the third session, we have discussed about measurements of matter, mass, weight, volume, density, and temperature. Learning outcomes. Students, at the end of this session, you will be able to use the scientific notation and perform simple mathematic operations on number and differentiate between precisions and accuracy. And you will be able to determine significant figures and to convert physical quantities from one system of unit to another. Uncertainty in measurements. Students, we know that chemistry is the study of atoms and molecules, and they have extremely low masses but present in an extremely very large number. Just to express 2 grams of hydrogen gas, we need to express it in such a long number. And not only that, to express a mass of hydrogen atom, we have to express it in a very long decimal number. Similarly, constants like Planck's constant, speed of light, charge of particles are to be expressed in extremely large numbers. So to handle such a very small and a large values, scientific notations are used. Problems to express large number is solved by scientific notation. In scientific notation, exponential forms are used which are represented in the form capital N into 10 to the power of small n, where small n is an exponent having positive or negative values and capital N is a number which varies from 1 to 9. Scientific notation. First, let us see the decimal point in the scientific notation. Decimal points move to left. Consider the number 232.508. We can write it as 2.32508 into 10 to the power of 2. If the decimal point moves 2 places to the left hand side, then the exponent is 2. We need to write it as 10 to the power of 2 in the scientific notation. Next, decimal points moves to right. Consider the number 0.00016. It can be written as 1.6 into 10 to the power of minus 4. Here, the decimal points moves 4 places to the right hand side. So, the exponent is minus 4. So, we need to write it as 10 to the power of minus 4 in the scientific notation. During the conversion of scientific notation, if the decimal points moves left, the exponent goes up. If the decimal points moves right, the exponent goes down. Multiplication in scientific notation. These two same rules to be followed to express the multiples in the scientific notation. First, let us consider this number 5.6 into 10 to the power of 5 into 6.9 into 10 to the power of 8. So we can add the powers if the base is same. So this 10 we can take it as a common one. Then 5.6 into 6.9 into 10 to the power of 5 plus 8. Then 5.6 into 6.9 into 10 to the power of 5 plus 8 is 13. So we have written as 13. Then when we multiply this 5.6 into 6.9, we get 38.64 into 10 to the power of 13. If we want to move this decimal one place to the left hand side, then we have to add plus 1 in the exponent form. So the number will become 3.864 into 10 to the power of 14. Coming to the next one, 9.8 into 10 to the power of minus 2 into 2.5 into 10 to the power of minus 6. So here also we can add the power since we have the same base as 10. Now we can take this 10 as a common one and 9.8 into 2.5 into 10 to the power of minus 2 plus minus 6. Then the exponent will become 10 to the power of minus 8. When we multiply these two decimals, we get 24.50 into 10 to the power of minus 8. Now we are going to move this decimal one place to the left hand side. So what we have to do? We have to add plus 1 in the exponent form. So 2.450 into 10 to the power of minus 8 plus 1. So here it will become 2.450 into 10 to the power of minus 8 plus 1 is minus 7. So if we want to move the decimal place one place to the left hand side, we have to add plus 1 in the exponent form. The same rule has to be followed to express the division in the scientific notation. So here let us take this number 2.7 into 10 to the power of minus 3 upon 5.5 into 10 to the power of plus 4, right? Here the 10 to the power of plus 4 is in the denominator. When it comes to the numerator, it becomes minus 4. Okay, so 2.7 divided by 5.5. Since the base is the same base, we can take 10 as a common one, minus 3 plus minus 4. Why minus 4? Here the denominator, when it comes to the numerator, we need to change the sign. So if we divide 2.7 by 5.5, we get 0.4909 into 10 to the power of minus 3 minus 4 is minus 7. Now if you want to move this decimal one digit to the right hand side, then the exponent goes down. That means we have to add minus 1 to the exponent form. So 4.909 into 10 to the power of minus 7 plus minus 1. What is minus 7 plus minus 1? That is nothing but minus 8. So we have to write it as 4.909 into 10 to the power of minus 8. Addition in scientific notation. For addition and subtraction in scientific notation, we have to write the numbers in such a way that they should have the same exponent. For example, 6.65 into 10 to the power of 4 and 8.95 into 10 to the power of 3 we are having. So what we need to do, we have to write this number in such a way that they should possess the same exponent. So 6.65 into 10 to the power of 4 plus, when we move one decimal to the left hand side, automatically we have to add one number to the exponent. So we can write 0.895 into 10 to the power of 4. Now we can take this 10 to the power of 4 as a common one and add these two decimals. Then we will get 7.545 into 10 to the power of 4. Subtraction in scientific notation. The subtraction of two numbers can be done as follows. Let us consider this number 2.5 into 10 to the power of minus 2 minus 4.8 into 10 to the power of minus 3. Now we need to write this number in such a way that they should have the same exponent. So 2.5 into 10 to the power of minus 2. When we move this decimal one place to the left hand side, we need to add plus 1 in the exponent. So 0.48 into 10 to the power of minus 3 plus 1 is minus 2. Now we can take this minus 2 as a common one, and 2.5 minus 0.48 will give 2.02 into 10 to the power of minus 2. Significant figure. Significance means meaningful digits. In chemical calculations, the experimental result should be accurate and precise. Precision refers to the closeness of various measurements for the same quantity, and accuracy is the agreement of a particular value to the true value of the result. Let us see these two concepts in detail. This is the pictorial representation for precision and accuracy. We have to assume the center point is the true value of an experiment, and the blue marks are the experimental results that we obtain. Accuracy refers how close the measurement to the accepted value. Precision refers the closeness of the measurement to each other. If the blue marks represents the results of the experiment, picture 1 shows us the results are precise but not accurate. Picture 2 depicts the results are accurate but not precise. Picture 3 shows the results are neither accurate nor precise. Picture 4 depicts the results are precise and accurate. Precision and accuracy can be more clearly understood from the data given in the table. For example, if the true value for a result is 2 gram, if student A reports two values for an experiment as 1.95 gram and 1.93 gram, then his value is precise but not accurate. If student B reports two values for the same experiment as 1.94 gram and 2.05 gram, his value is neither precise nor accurate. If student C reports two values for the same experiment as 2.01 gram and 1.99 gram, then his values are both precise and accurate. Certain digits and uncertain digits. Experimental measurements have some amount of uncertainty. For example, mass of an object obtained by platform balance vary from analytical balance. The uncertainty values is indicated by mentioning the numbers of significant figures. Significant figures are meaningful digits which are known with certainty, and it is indicated by writing certain digits first and the uncertain digits after the decimal point. If the mass obtained is 9.3, then 9 is the certain digits and the number 3 after the decimal point is uncertain digit, and it would be plus or minus 1 in the last digit. There are certain rules for determining the number of significant figures. All non-zero digits are significant. For example, 285 centimeter has three significant figures and 0.25 ml has two significant figures. Next, zeros preceding to the first non-zero digit are non-significant. For example, 0.03 has one significant figure and 0.0052 has two significant figures. Zeros between two non-zero digits are significant. Here they have given 2.005. We have two zeros in between two non-zero digits. So totally we have four digits. So this number has four significant figures. Then 0 on the right side of the decimal, that is 0 at the end or the right of a number. It should be on the right side of the decimal or significant. For example, if we take 100, there is no decimal. So this number 100 has only one significant figure. But in the case of 100 point, it has three significant figures, and 100.0 has four significant figures because it has one zero after the decimal point. Zero after the decimal point are considered as a significant figures. Scientific notations for the following numbers can be represented as, we can write 100 as 1 into 10 to the power of 2. There is no decimal point over here. So it has only one significant figure. 1.0 into 10 to the power of 2. Since there are two numbers and we have 1 0 after the decimal point, this number has two significant figures. 1.00 into 10 to the power of 2. There are two zeros after the decimal point. So this number has three significant figures. Counting number of objects like 2 balls or 20 eggs have infinite significant figures because these figures are exact numbers. It can be represented by writing infinite number of zeros after placing a decimal. For example, we can write 2 is equal to 2 point so many zeros we can add, and 20 is equal to 20 point. We can add so many zeros after the decimal point. all the numbers in the scientific notations or significant figures. For example, 4.01 into 10 to the power of 2 has three significant figures. 8.256 into 10 to the power of minus 3 has four significant figures. So all the numbers in the scientific notations are significant figures. The results cannot have more digits to the right of the decimal point than either of the original numbers. Here we have three numbers. In these three numbers, we have 18.0. This 18.0 has only one digit after the decimal point. So the result should be reported up to only one digit after the decimal point, which is 31.1. Rounding of the numbers in the significant figures. Let us consider this number. 2.5 into 1.25 gives 3.125. Since 2.5 has two significant figures, the result should not have more than two significant figures. So the result is 3.1. Now let us take another number 1.386. For example, to remove the last number 6 from 1.386, we have to round it to 1.39. If it is greater than 5, then we have to round it as 1.39. Consider the number 4.334. To remove the number which is less than 5, here we are going to remove 4. We have to round it as 4.33. Now, if you want to remove a number 5 from an odd number, here before this 5, we have an odd number. To remove a number 5 from an odd number, we have to round it as 6.4. However, to remove 5 from 6.25, here we have even number. So to remove this 5 from an even number, we have to round it as 6.2, not 6.3. Dimensional analysis. During scientific calculation, there is a need to convert units from one system to another. The method used to accomplish this is called factor label method or unit factor method or dimensional method. Here one example we have given 1 centimeter equal to 0.3937 inch. 1 inch is equal to 2.54 centimeter. Let us see some example sums under the concept dimensional analysis. A piece of metal is 3 inch. They have given in inch. What is its length in centimeter? So we need to give the answer in centimeter. We know that 1 inch equal to 2.54 centimeter. So this equivalent can be written as 1 upon 2.54 equal to 1, which is equal to 2.54 centimeter upon 1 inch. So both of these are unit factors and 3 inch has given in the above problems. So we need to express in centimeter. So we need to take this as the unit factor for this problem. So 3 inch equal to 2.54 by 1 inch. The inch and inch get cancelled and 3 into 2.54 centimeter divided by 1, that is equal to 7.26 centimeter. Now the unit factor by which multiplication is to be done is the unit factor in the above case. Second problem, the jug contains 2 liters of milk. Calculate the volume of the milk in meter cube. We know that liter is not an SI unit, but we know the conversion 1 liter is equal to 1000 centimeter cube. We need to give the answer in meter cube. So we have to use the conversion 100 centimeter equal to 1 meter. From this equivalent, we can write the unit factors 1 meter upon 100 centimeter equal to 1, that is equal to 100 centimeter upon 1 meter. Since we need to give the answer in meter cube, we have to take the first unit factor for this problem. To get meter from the above unit factors, the first unit is taken and it is cubed. 1 meter by 100 centimeter. So when we cube this 100 centimeter, it become 10 to the power of 6 centimeter cube. 1 meter cube upon 10 to the power of 6 centimeter cube. In the problem, they have given 2 liters. So we have to convert it into 2 into 1000 centimeter cube. So multiply it by the unit factor. 2 into 1000 centimeter cube into the unit factor. This is equal to this centimeter cube and this centimeter cube get cancelled. So 2 into 1000 into 1 meter cube divided by 10 to the power of 6 means 6 zeros are there. So we can cancel these 3 zeros and 3 zeros in the denominator. So it will become 2 into 1 meter cube is equal to 2 meter cube upon 10 to the power of 3. So when this 10 to the power of plus 3 in the denominator, when it goes to the numerator, it will become 10 to the power of minus 3. So 2 into 10 to the power of minus 3 meter cube. The third problem, how many seconds are there in 2 days? So we need to convert days into seconds. We know that 1 day is equal to 24 hours, 1 hour is equal to 60 minutes, and 1 minute is equal to 60 seconds. So we have 3 unit factors for this problem. So for converting 2 days to seconds, we need to use all the 3 unit factors. The unit factors can be multiplied in series in one step as follows. 2 days into 24 hours upon 1 day into 60 minutes upon 1 hour into 60 seconds upon 1 minute. So that is equal to 2 into 24 into 60 into 60 seconds. That is equal to 172,800 seconds. Students, let's recall what are all the concepts that we have discussed in this session. Scientific notation is the convenient system to express the measurement of quantities in chemistry. Then significant figures we have discussed, which helps us to express the uncertainty in experimental values. Then finally, dimensional analysis helps us to express the measured quantities in different system of units. These are all the concepts that we have discussed in this session. Hope this session is very useful to you. See you soon in the next session. Have a nice day. Thank you.